Okay, let's get started. Today is our a great pleasure to have Professor Osting here. Professor Osting graduated from Columbia University, and he was a postdoc at the UCLA, and we met there. Uh, he's now associate professor in the Department of Mathematics at the University of Utah. He has a very broad interest in analytical and computational methods for problems in applied mathematics, especially in partial differential equations, optimization and control, graph theory, and machine learning. So, Braxton, so please.
Yeah, thank you very much, Ranji, and thanks for inviting me to give this talk. I've never visited RPI, so I'd love to be able to visit it.
You should visit after we go back to normal.
When this is over. So I hope you can see my screen. I'm going to talk about consistency of archetypal analysis today, and of course I'll explain what archetypal analysis is. But this is joint work with Yiming Xu, who's a graduate student here at the University of Utah, Dong Wang, who was my former postdoc and is now an assistant professor at the Chinese University of Hong Kong in Shenzhen, and then Dominique Zosso, who was, who Ranji knows, who is also a postdoc at UCLA and now is at Montana State University. Okay, so let me begin by saying what archetypal analysis is. And at a high level, it's an unsupervised learning method that approximates or summarizes multivariate data using a convex polytope. So you're given data X, and these are going to be points in RD throughout this talk, and I'll say I'll have n of them. And you also fix an integer k. K is going to be the number of vertices in this convex polytope that you're using to summarize the data. All right, so you're given the data, and then you find a cardinality k point set A, and A are really just the vertices of this polytope. So I'm finding a polytope that, that solves this optimization problem. So the objective function here is I look at the mean squared distance between the data and the convex polytope. So it's the convex hull of these k points. The k points are the vertices. And I have the constraint that each of the k points are contained in the convex hull of the data. Okay. All right. And so maybe it's best to illustrate this idea with a picture. So here on the right, let's see. I have the data. Those are the blue points. So these are points in just 2 dimensions. Now I fix the integer k. That's 3 in this case. I'm looking for a triangle. And I want to approximate the data with the triangle. And so what the objective does, the objective function, is it measures the mean square distance between the data and the polytope. And so like for this point here, I measure the distance between the point and polytope. Well, I take the convex projection of the point onto the polytope, and then I just look at this distance, right? And I square it and sum them over the points, and that's my objective function, right? And so, of course, if the triangle contains the point, then the point doesn't contribute to the sum. So that's desired. And so you can imagine that what this triangle wants to do is just kind of grow as much as it can. Of course, it's constrained to stay in the convex hull of the data, right? That's this constraint. It grows as much as it can so that to minimize this mean distance to the points. Okay. And so you can see that actually this triangle is not optimal. I could move this triangle, this vertex here, a little bit down and to the right, and the objective function would decrease. Okay. So after I solve this optimization problem, I'm going to just attach the adjective archetype to everything involved with that solution. So the optimal point set, I'm going to call the archetype points. The convex hull of those points is going to be the archetype polytope. If I'm in 2 dimensions, I'll call this the archetype polygon or the archetype triangle if it's, k is equal to 3. Okay, so that's the language I'm going to use. All right, so this method, I'll say a few words about it. This was introduced in 94 by Cutler and Bryman, and they proved quite a few results for the method. The first thing is if k is equal to 1, so there's only one archetype point, you can show that that point is the mean of the data. So that's not surprising, right? This is the closest point to all the data. The problem is interesting when k is between 1 and n. Remember, n is the number of data points. And so in this case, they proved existence of an archetype point set. And generally, the archetype point set is not unique, but they showed that there exists one solution, one archetype point set on the boundary of the convex hull. Right? So this captures this notion that this archetype polytope wants to just grow and be as large as possible within the constraint set. And then finally, if you take k greater than n, k is the number of vertices is greater than the number of points, well then the problem becomes boring again, because well, the optimal solution is just given by where you take the point set to be just the data, right? So this has objective value 0, and yeah, so the typical use case is when the number of vertices k is it's smaller than the number of data points, and often it'll be smaller than the dimension d as well. Okay. They also demonstrated that archetypal analysis can be reformulated as a nonlinear least squares problem and efficiently solved using an alternating minimization algorithm. So I'll say a little bit more about this later. I just want to attribute it to them at this point. And this method is also sometimes referred to as principal convex hull analysis. So I won't use this language, but in case you've seen it in that context before. Okay. So the way I've described archetypal analysis, I would call this kind of the geometric formulation of this. And so this is exactly what I wrote on the previous slide. I just want to emphasize that there's also an algebraic formulation of this. So here I would construct a matrix X, and the columns of this matrix are going to be the data points. And then I can rewrite archetypal analysis as this non-negative matrix factorization problem, where I want to find matrices A and B so that X is equal to X times A times B. And the constraints on A and B are, well, that these matrices should be stochastic vectors, so that they're non-negative and they sum to 1. And let's see, if you think about this, you can see the correspondence. Let's see, X minus XAB. So XAB is going to be the convex projection of, like, the columns of XAB are going to be the convex projection of each of the data points onto the convex polytope. And so XA, since A is column stochastic, XA, these are going to be, the columns of that are going to be the archetype points themselves. And so A is an expression of, like, how do you express the vertices in terms of convex combinations of the data. And then B tells you how you express the convex projection of the data, in terms of the archetype points, right? So, well, if you think about this for a minute, I think you'll see these are equivalent problems. So you have this nice non-negative matrix factorization formulation of the problem. Okay. So I'll say a couple more general things about this method. Let me first just compare it to other unsupervised learning methods that you're probably much more familiar with. Let's see. So I said archetypal analysis has these, like, the geometric formulation and the algebraic formulation. And I think about archetypal analysis as I'm trying to find extreme patterns within the data. Right? Like, so these archetype points, these are kind of very extreme examples of points in the data. And then I can think about the data in relation to those extreme points. In clustering, you're trying to do something slightly different. In clustering, you're kind of looking for prototypical rather than archetypal points, examples. And so you're looking for prototype points, and then k-means, this is the formulation of k-means, and this is written kind of geometrically. I'm trying to find a k-cardinality point set in the same dimension as the data. And I just look at this mean square distance between the data and that point set. So it's like I start with archetypal analysis and I just remove all of these convex hulls. Right? So I don't look at the convex hull of the point set, I just look at the point itself, right? And k-means, you also don't have to constrain the points to be in the convex hull of the data. That actually is something you can prove. You can prove that that naturally happens. Okay, so that's the relationship between archetypal analysis and k-means. The other unsupervised learning method that this has a lot in common with is principal component analysis, PCA, right? So in PCA, you start with data in generally a high dimension, and you try to find a low dimensional representation of the data. And so there's a geometric and algebraic formulation of that problem. The geometric formulation is I try to find the k-dimensional subspace so that when I look at the projection of the data onto that subspace, say V, I look at those projected points and I measure the covariance, and I try to find the subspace to maximize the Frobenius norm of the covariance. And so that's the geometric. So geometrically, I'm looking for a high covariance subspace that I can project the data onto. And algebraically, I can form this as, again, a factorization problem. I take the data X, and I want to find a matrix U. The U in this case, this is a tall, skinny matrix with orthonormal columns, and I try to find the matrix U so that X is nearly XUU transpose, right? And so if you look at the algebraic formulation of archetypal analysis and PCA, these are very similar, right? I just have different constraints on this matrix that I'm trying to use to factorize X. And geometrically, I can also compare archetypal analysis and PCA. PCA, right here I have points in 3 dimensions, and I'm projecting them onto this 2-dimensional subspace. In archetypal analysis, if I choose, in this case, k is equal to 3, so there's 3 vertices here, I just have a triangle in 3 dimensions. This does dimensionality reduction at the same time as it finds this optimal triangle, because the triangle is 2 dimensions and the ambient dimension is 3 dimensions, right? And so at the same time I am reducing the dimension of the data, I'm also finding these extreme examples of the data, right? And so now, after I have solved this archetypal analysis problem, I can interpret all of these points in terms of their, how are they compared to the extreme points in the data. Okay, so there's a lot of further discussion about archetypal analysis in terms of other matrix factorization and clustering methods in this nice review paper by Morup and Hansen. Are there any, maybe I should pause and see if there's any questions at this point. I'm also going to give an example of how you would apply archetypal analysis in an application. Okay, so if not, so let me talk about this example. And so, of course, now you have to use COVID data as an example. And so this data set, it's from the early days of the pandemic, and it has the positivity rate from, let's see, May to September for 51, the 50 states in DC. So there's 51 examples here. And, there's 4 months of data here, so it's of daily data, so it's maybe 120 dimensional. The original data is in 120 dimensions if you want to view the time series like that. And if you do principal component analysis on this data, what you find is that, 99% of the variance can be captured in just the first 2 principal components. Okay, so this is, even though it's a 120 dimensional data set, really there's 2 dimensions of data here. So this is a nice example for visualization purposes. And so let's see what happens when you apply archetypal analysis to this data. And I do want to just point out, I think this is New York here, this one that starts very high. So they had this very bad first wave, right? And then Arizona leads with the second wave here. So this is Arizona here. Okay, so we'll interpret this later. Okay, so here, here I'm going to show the results of archetypal analysis for this data. And
Sorry, can I just ask a clarification?
Yeah, sure.
Yeah, so do we think about this as a 51-dimensional data set and every day is giving a separate data point?
No, sorry. I want you to think about this as 51 data points in 120 dimensional space. So each dimension corresponds to a different day.
Okay, thanks.
Okay, so I want to do archetypal analysis for this data set. And for visualization purposes, I'm going to do something that you wouldn't necessarily do in practice, but I'm going to first reduce the 120 dimensions to 2 dimensions by projecting onto the principal components. And then I'm going to do archetypal analysis. The way you would do this in practice would be to just do archetypal analysis from the beginning. So here's that data set in terms of the principal components. So you have the first 2 principal components here. And yeah, so here you can see, here's a bunch of northeastern states. New York is right here. Here you have Arizona. This is leading the second wave here. And then you have a bunch of states where well, kind of at least initially the positivity rates were uniformly low over time. So that's how I would kind of interpret this. And so these points, so I want to use k equal to 3 archetype points. So I'm trying to find a triangle that approximates this data set. And well, that's the red triangle here. The blue triangle is the data. And let's see. One thing you can see, and this is maybe something to point out, is that the archetype points aren't necessarily in the original data set. So there's no state that corresponds to this archetype point. But Arizona would be the closest point in the data that corresponds to that archetype point. But that's not always true. Like, for example, Alaska is, this archetype point corresponds to, is the same point as Alaska here. And then after you find the best triangle in this case, you can, well, you can at least, if it's such that your archetype polytope is a simplex, then you can think about kind of archetype coordinates, right? And so I can represent this in terms of the archetype points. I can now transform and look at convex combinations of these archetype points, and then so this is just an equilateral triangle in this case, and generally it would be a simplex. So this is a nice way to visualize it, because I can see now that, well, I can just see that the Northeast is one archetype, Arizona is another, and then I have these uniformly low ones. And for a state like Utah here, Utah initially had very low positivity rates, and then had a medium second wave. And so I can kind of interpret Utah as some kind of combination of these states like Alaska and states like Arizona. Okay, and so I think this is more interpretable in many cases than the PCA analysis. If I were just to look at the PCA coordinates here, I wouldn't necessarily have much meaning for PCA coordinates, right? I mean, you can do this sometimes. Sometimes you can interpret the principal components, but in many cases, especially if you don't have that low dimensional representation of the points, then it's difficult to assign interpretation to the principal components. And so just to drive this home one more time, when I look at the states near each of the archetype points, so these are the red, blue, and orange curves, these are coming from, these are exactly the states corresponding that are very near one of the archetype points. And so you see very different behavior in the original time series for these states. So any questions about this example?
Yeah, this is quite interesting. So this is always the case. You have this simplex structure, and each extreme point of this, each vertices of this simplex will means something, or this just for this example.
Well, that's the dream, right?
That's the dream. Okay.
The dream is that I get the dimensionality reduction at the same time that's interpretable, and so maybe it doesn't always work, but yeah, there's many cases where it does. And actually, if you go back to that paper that I referenced earlier by Morp and Hansen, they have quite a few examples in that of all kinds of data, of image data and other kinds of data where you can successfully get an interpretation of these archetype points.
But if you don't do the PCA first, directly conduct this on the original space, would this result still consistent, or I guess?
Yeah, you can still do that. It's harder to interpret this if the number of vertices is greater than the dimension. So like if I were to have a two-dimensional space and then look for 4 vertices, I have quadrilaterals here, then it's more difficult to kind of visual, like the convex, the representation in terms of the vertices is not unique, right?
Yeah, but even in height, you can still choose three points, right? Then they still form a.
Exactly. Yeah. So this picture on the left would look the same in the 120 dimensional space. It's just that you just have a triangle there, and then the other spaces would all orthogonal. Yeah. And actually, if you're in a 120 dimensional space, maybe, and then you can use more vertices, right? You could have a 4 or 5 simplex and have a nice representation of the data too.
Mm-hmm. Mm-hmm.
I'm sorry if you said this already, but is there guidance on why k equals 3 is a good choice versus k equals 4 or 5?
Well, this is like choosing the number of principal components, right?
Right.
It's
But is there a score you can look at to sort of give you guidance, like there's a rapid fall off of value after you get past a certain point?
Oh yeah, definitely. That's a good point. I mean, this is the solution of an optimization problem. So I can look at the objective function for different values of k, and yeah, if you want to do this kind of knee analysis, that would be one way of choosing k. Definitely.
But this is slightly different from PCA, right? PCA, you choose k is equal to 3 or k is equal to 4. The first 3 components, they're consistent. But here, if you choose different size of A, this is not linear. So you may not get a consistent result.
That's right. That's right. So it's true. If you, as you increase the number of principal components, you kind of add directions and not affect the first directions, right? And so here, if you add a new vertex to the polytope, it could move the previous vertices you've already found. That's exactly right. Okay, so what I want to talk about today is a consistency result for this method. And I'll say a couple of words that are general about consistency in statistics. And so generally for a consistency result, you start with, the consistency result is for a method applied to data. So I'm looking at this kind of bottom left-hand corner here, and I have some discrete archetypal analysis. The archetypal analysis I want to attach this word discrete to, and I do this analysis and I come up with the solution, which is this red triangle here. And so in a consistency result, you come up with a statistical assumption about the generation of the data. So I'm gonna assume that these points are sampled from some distribution, and then I'm gonna find a continuous problem that gives me a triangle for the continuous problem. And what I want to show is that as I sample more and more points here, the triangle in the discrete setting converges to the triangle in the continuous setting. Okay, that's going to be the consistency result here. And so generally, you have to do a little bit of work for consistency result. You have to define the statistical assumption about the generation of data. You need to identify the mathematical object that you're going to converge to. You have to talk about what the notion of convergence is, and then of course, whenever you have convergence, the next thing you ask about a convergence rate, right? And so you want to know is as you increase the sample size, what's the rate of convergence to the continuous object? Okay, so that's what I want to establish for archetypal analysis. And I'll say, the consistency result that everyone has learned is that the sample mean converges to the population mean as the number of points goes to infinity, at least. And this is what the law of large numbers tells you, right? So that's an example of a consistency result, but these have been there's consistency results for a lot of different methods in statistics, and so some for unsupervised learning methods. There's a result by Pollard from the 80s that established it for k-means clustering. The PCA results are now classical. This has been proved for spectral clustering, and then I'll draw attention to work I did with Jeff Calder and his student Amber Yuan just this last year. We established consistency for the PageRank algorithm. Okay, so let's talk about this for archetypal analysis. And so, of course, I'm going to assume that my data is IID sampled from a probability measure mu. And now I'm going to decorate my solution to the archetypal analysis problem with an n, right? So for each n, so after I've sampled n points, I'm going to compute my optimal polytope, and I'm going to call that an. And so then my question, the consistency question is there a set A so that an converges to A in some sense is my number of points n goes to infinity? All right, so to identify the limiting problem, it's useful just to rewrite this sum as an integral with respect to the empirical measure. So I can just write I can just rewrite the objective function in this way. And mu of n is just the sum of direct deltas centered at each of my data, right? This is the empirical measure. And since the empirical measure weakly converges to the probability measure mu as n goes to infinity, it's natural to consider the limiting problem where I just replace in the objective function the empirical measure by mu. Right. So this is going to be my this is going to define the solution to this optimization problem here. This is going to define my object that I'm going to converge to. Right. My A of n are going to converge to this A. At least that's the hope. Right. That would be the consistency result. And so this is exactly what we can prove. So I want to first address the case when mu has bounded support. So my mu is my probability. This is the measure that I'm sampling points from. So if this has compact support and a density, and I'm assuming my data, sampled IID from it, what we can prove is for each n, the archetypal analysis problem has at least one solution, A of n. Of course, okay, so this was already known by Cutler and Bryman. We can prove that along a subsequence, the A of n converge to A star in the Hausdorff distance. So A star is exactly the solution to the problem that I just had on the previous slide. And we also get a rate. So we prove that if the support of mu is convex, then for large n with high probability, the value of the objective functions, the optimal objective values, this converges at a rate bounded by this quantity here. And so I'll comment a little bit later. Let's see, this assumption that the support of mu is convex can be relaxed a little bit, but I'm stating that like the simplest case here. So there's a more general assumption that can be made, and that's discussed in our paper. Okay, so that's our consistency result when the measure has bounded support, and I'll just comment on the proof. I won't go through this carefully today. Let's see. The existence just comes from continuity and compactness, and this compactness here we're using that the measure has bounded support. Consistency again just uses compactness and the triangle inequality. So this is, I've written it very simply here. This is a couple of pages of estimates. You have to use the triangle inequality in kind of a tricky way, but in the end it just boils down to the triangle inequality. And then the convergence rate is harder. You need to use a result from random geometry and Dudley's inequality, and this will give you the convergence rate. And so a couple of remarks on the proof in this theorem. Compactness is necessary for the problem to make sense. And if you just think about this for a second, if I have a distribution with unbounded support, then, maybe with low probability, but, I'll occasionally get points kind of further and further from the origin, right? And so my constraint set on the polytope is growing. And so, my polytope will continue to grow, and, it's not going to converge to anything, right? And so I need this bounded support on the distribution in order to for this problem to make sense and to get a consistency result. The other thing I want to make remark on is minimizers are not unique in general. So I mentioned this before, but you can, if mu is the uniform distribution of the unit disk, we proved that, well, when I fix k, the solution is a regular k-gon inscribed in the disk. And so this is also why I have to state this kind of carefully. I have to say along a subsequence because, well, the minimizers are not generally unique. And then, okay, I already commented on this. The convexity assumption can be relaxed. And we talk about this in the paper. We have this alpha cap condition that's more general. So you might want to ask then what happens if the support of the measure is unbounded. And I already said what the problem is. If the convex hull of the data continues to grow and is unbounded, then well, you're not going to have consistency for the archetype polytopes. And so somehow we have to modify this method in order to get a consistency result. And so the modification that we used here was to introduce a regularization term that just prevents the dispersion of the archetypes. So it just somehow prevents the archetype polytope from just getting larger and larger. And so the regularization term we introduced is just to look at the variance of the archetype points themselves. So what these are the vertices of the polytope, and I just look at the variance of them. So I subtract the mean and sum the squared distances. And so, of course, with the regularization term, I have to introduce this new parameter alpha, and well, of course, I have to choose that, or I get to choose it depending on your viewpoint. So let me call this the variance regularized archetypal analysis, this modification of the problem. And we have a consistency result for this too. So if mu can have unbounded support, but let's suppose it's square integrable, and again, I IID sample points from it, then well, you can show that for each n, again, the variance regularized archetypal analysis problem has at least one solution. And then under the assumption, that mu almost surely for any radius r, there exists some integer so that the ball of radius r is contained in the convex hull of the data set, with n points. Under that assumption, I have, again, the convergence and the Hausdorff distance of the solution to this regularized problem to a continuous problem, and a continuous problem is exactly the one you would think it would be. It's just replacing the empirical measure by mu and then also adding this same regularization term. And so in this case, we could also say something about the dependence on alpha. So for large alpha, we can say that the largest distance between an archetype point and the mean of the original data, this is going to zero at a rate, the distance is going to zero at a rate alpha to the minus 1/4. And so this makes sense, right? As alpha increases, the second term is going to dominate, right? And that just means that all of the archetype points are going to go to their mean. And where is the mean going to be? It's going to be the mean of the original data, right? And so you have all the archetype points going to the mean of the original data, and this just captures the rate at which that happens. All right. Okay, so let's I'll mention how we compute solutions to this problem, and then I'll give some numerical examples. So I mentioned this before, so this is something that Cutler and Brightman already wrote down, is this alternating method for solving this problem. And so we solve the subproblems differently than they do, but they look the same alternating method. And so so I mentioned that you can rewrite this the archetype analysis problem as a non-negative matrix factorization problem. This is the kind of the algebraic formulation of this, as I presented earlier. And so the way this works is I just alternatively solve for the matrices A and B. And so writing Z is equal to X times A, I can solve for B. And I think it's pretty clear that this problem is just solving a least squares problem under the constraints that the columns of B are in the unit simplex. And so you can solve this problem using the projected gradient descent method, where I alternatively, improve B and then project onto the unit simplex. And those are both very efficient steps. And then the second problem, A is sandwiched between X and B, but actually you can rewrite this and you can see that this is also just a least squares problem, and the constraint set is exactly the same. So yeah, this can also efficiently be solved, and by alternating these two convex problems, you can find the solution to the archetypal analysis problem. So let me show a couple of examples that that just illustrates this. So the first one is I want to show consistency, or illustrate consistency. So I start with the unit disk with the uniform distribution on it, and we know that the solution to that problem is an equilateral triangle inscribed in the unit disk, and that's exactly what we see in the numerics too. And so as I sample more and more points, this is n here. As I sample points, the minimum and the maximum angle of the triangle goes to the angle for the equilateral triangle pi over 3. Okay, so this is showing that, it's just illustrating the consistency result. And then here's another numerical simulation where we investigate the dependence on the regularization parameter alpha. So remember, alpha is this regularization parameter that gives a trade-off between the original objective function and the variance of the archetype points. And so here, let's see, I have just points sampled from a normal distribution. So the points are fixed. And I drew the convex hull here of the points. And for fixed alpha, I can solve this problem. And that's this triangle. So k is equal to 3 here. Here's the triangle solution there. And so you can already see the effect of the regularization just because this triangle, the vertices of the triangle are not on the boundary of this, on the convex hull of the data. They're already kind of inside, it's strictly inside the interior of the convex hull. And as we crank up alpha, so this is alpha here, this archetype triangle shrinks, and eventually, and gets very close to the mean. The mean is the black dot here, and so it's approaching the black dot as alpha goes to it gets large, and the rate is consistent with the result I just gave. Okay, and so so what we've done is for bounded distributions, we've identified a continuum problem of archetypal analysis and established a consistency result, including the convergence rate. And for unbounded distributions, we introduced a variance regularized problem and established a consistency result. And we also investigated how solutions depend on the regularization parameter. And there's a couple future directions that I want to go in. And actually, I have a couple more slides that describe these in a little bit more detail. One is to consider another way to modify archetypal analysis by replacing the objective function. Instead of using the Euclidean distance, I want to use the Wasserstein distance. And then the other future direction that I'm really interested in is to investigate what's called deep archetypal analysis. So this is instead of looking for a polytope in the original space, it's looking for a polytope in the latent space for an autoencoder. So I'll say a little bit more about that in a second. So I'll just say that everything I presented so far is was published in the Siam Journal of Mathematics of Data Science. So let me say a little bit more about this Wasserstein problem. So here, this is work that we're currently doing. So these are very preliminary results. But this is work with Katie Craig at UCSB, and also Dong and Yiming, who I already mentioned. And here, given a probability to measure mu, so this is again, and this could be an empirical measure for a collection of data, or generally some other probability measure. What we do is we're still trying to approximate mu by a convex polytope, but here we do it in the way where we consider the uniform distribution on the set of convex polytopes, and then we find the convex polytope that minimizes the Wasserstein 2 distance between mu and the uniform distribution on a polytope. And so the interesting thing about this is it's no longer necessary to require that the polytope be in the convex hull of the support of the measure mu. That's taken care of by the Wasserstein distance. And well, I say this problem can be solved, at least in small dimensions, by reformulating it as a semi-discrete optimal transport problem. And so we have some initial results. And one thing that's really, I mean, this is one of our motivations, but it's also one thing that we observe is this problem is much less sensitive to outliers than using the Euclidean distance. And so this is one of the complaints, I think, in general about archetypal analysis. If I have data points that are all kind of localized, and then I introduce an outlier way over here, that archetype polytope is going to pay a lot of attention to that outlier, right? Like it's going to grow in some way that's probably undesirable. And so one way to fix this would be to use this variance regularization term that we already introduced, but the Wasserstein metric does this, and I think it does it in a more natural way. It feels very artificial maybe to introduce a variance regularization. And so here I have a couple of images just to illustrate this. And so if I have data that's mostly concentrated on this triangle here, and then I have just a couple more outliers, the Euclidean distance is going to pay attention to those outliers, and it's just going to give you this red triangle, right? But the Wasserstein metric, it would have to pay a lot. The red triangle is not going to be optimal for the Wasserstein metric because it's going to have to pay a lot to transport mass, from the bulk to like points in the red triangle where there's no points, right? And so actually the blue triangle will be nearly optimal for the Wasserstein metric. And you see that play out. So here's a numerical example. The red triangle here, this is the solution using Euclidean distance, the original archetypal analysis, and the black triangle here is the solution using the Wasserstein metric. And so, yeah, here you see the same kind of effect as this variance regularization gave you before. Let's just say the caveat, one downside is that maybe it's a little bit more difficult to interpret the extreme points of this Wasserstein archetypal analysis, right? Since these are no longer extreme in the original data set, they're almost extreme, or some kind of like regularized extreme. So I think this is this has been a fun project, and it's been rewarding for me because I've learned a lot more about the Wasserstein metric. Katie Craig is the real expert on this team on that. And then I'll mention this other future direction, and this is deep archetypal analysis. And so here's another idea. Here, an autocoder is designed so that the encoded points in the latent space lie within a fixed archetypal polytope. And so let me just say a couple of things about autocoders. Autoencoders are what? It's two neural networks. You have an encoder and a decoder. And you think about this as you have high dimensional points. And when you encode them, you go to a low dimensional space. And then when you decode them, you go back to the original dimension. And you train the neural network so that this the composition of these two neural networks, this gives you nearly the identity, right? So people think about this as not much information is lost by going down a dimension and then up in dimension. And well, the twist for archetypal analysis, including this in the autoencoder, is that you no longer let that in the bottleneck, in the low dimensional latent space, you no longer let that be just Euclidean space. You actually fix that to be an archetypal polytope. And actually here you get to fix it. It can be just, for example, a unit simplex. Because you have a nonlinear transformation into that space, you can kind of let the archetype polytope be whatever. You can let it be a unit simplex, a canonical polytope. And the advantage to doing this, you're still going down in dimension when you use this, but now you gain some interpretation of in the latent space. So you're still reducing the dimension of the data, but you're getting some more interpretability of the encoding. And so yeah, on the right here, I have an example. And this is, there's a SLEB-A data set. You might have seen this. I think there's 200,000 images of celebrities, or and so these are images. I think they're like maybe 100 by 100 pixels. So the original dimension is maybe 10,000. And so if we use a 53-dimensional latent space, and then do this archetypal analysis, here's a selection of 9 archetype points from those 53, and these are not these are not necessarily faces in the original data set. Remember, archetype points don't have to correspond to the original data set point. So these are near faces in the latent space, or decoded from the latent space, and they're a little bit blurry. Okay, so this is an initial result, but you can see the idea. And well, these are very diverse faces. You have a hat here and sunglasses and all kinds of different expressions. And so you can now think about other faces in relation to these. And so this has been a fun project. And so I say this is an SRI undergraduate student project. So this is a new initiative at the University of Utah to engage undergraduate students at a very young age in research. And so Lam, Darshan, Tanner, and Grace on this project, they're all undergraduate students. And then RK Yoon is a graduate student of mine in math, and Rich Medina is in geography here at University of Utah. And well, he's involved because we're starting to use these tools to create interpretable latent spaces for automatically setting online hate speech. So he's an expert on online hate speech, and he has these data sets that, well, where white supremacists post all kinds of hate speech. And so the dream is to be able to automatically find patterns in these posts. And so we use NLP tools to embed each post. And then we use archetypal analysis to try to develop latent spaces that, well, you can identify really extreme language. So I think this is a fun project in future direction as well. So yeah, thanks. If you have any questions, I'm happy to take them.
Thanks so much. This is a very interesting talk.